Hello everyone. Welcome back to another exciting chapter in geometry. Let's begin with a simple question. Have you ever watched a car's tire touch the road? No matter how fast the car moves, at any instant, that tire touches the ground at just one single point. That point is the tangent contact. And today, we'll explore how many such tangents can be drawn from a point to a circle. Now, mathematically speaking, the number of tangents that can be drawn from a point to a circle depends on where that point is. If the point is outside the circle, you can draw two tangents. If it's on the circle, you can draw only one tangent. But if it's inside the circle, no tangents are possible at all. So, the geometry of tangents completely changes based on the point's position relative to the circle. And that's what makes this concept so fascinating. One simple rule, three distinct outcomes. Let's start with the first case, when the point lies outside the circle. Imagine a circle with center O and radius R. Now, take a point P outside the circle such that the distance OP is greater than R, that is, OPR. From that point P, we can draw two tangents touching the circle at points T1 and T2. And here's the interesting part. Both tangents are equal in length, which means PT1 equals PT2. Why does this happen? Because if you join OT1, OT2 and OP, the two triangles OPT1 and OPT2 become perfectly congruent by the RHS congruence rule, right angle, hypotenuse and one side. So, both tangents drawn from the same external point are equal. It's one of the most elegant and useful results in circle geometry. Now let's look at the second case, when the point lies on the circle itself. If you take a point T right on the circle, there is only one tangent possible at that point. This tangent will always be perpendicular to the radius drawn to the point of contact. So, if the radius is OT and a tangent touches at T, then the angle OTP equals 90 degrees. The condition for this case is OT equals R. This single tangent represents the boundary between two possible tangents and none. Move even slightly inside, and tangents disappear. Move slightly outside, and you get to tangents again. This perpendicular relationship between the tangent and the radius is the foundation of all tangent-based theorems that follow. Now, what if the point lies inside the circle? Let's say there's a point P inside a circle with center O and radius R. In this case, OP is less than R. That is, OPR, no matter how you draw a line through P, it will always cut the circle at 2 points. That means it can never touch the circle at just one point. So, mathematically, it's impossible to draw a tangent from an internal point to a circle. It's like trying to draw a straight line that just brushes the inside of a balloon. It'll always slice through instead of just touching. Let's organize what we've learned so far in a simple table. The number of tangents depends on the distance of the point from the center. If OPR, the point is outside, we get two tangents. If OP equals R, the point is on the circle, we get one tangent. If OPR, the point is inside, we get no tangent. So the relationship between the point and the circle can be summarized like this. Outside point two tangents. On the circle one tangent. Inside point no tangent. And this pattern is consistent for every circle, regardless of its size. It's a simple yet powerful classification that appears in both conceptual questions and board exam proofs. Now, let's take a practical example and calculate tangent lengths using the tangent condition formula. Given a circle with center O, radius R equals 5 centimeters, and an external point P such that OP equals 13 centimeters. We know from geometry that PT equals square root of bracket OP squared minus R squared bracket close. Substitute the values. PT equals square root of bracket 13 squared minus 5 squared bracket close. That is, square root of bracket 169 minus 25 bracket close equals square root of 144, which gives 12 centimeters. Hence, from point P, we can draw two tangents, each having a length of 12 centimeters. Simple logic, clean geometry. And that's exactly how you'll solve similar questions in your exams. Now, let's see where tangents appear in our daily life. When a bicycle wheel rolls on the road, the point of contact forms a tangent. In gear systems, teeth of one gear touch another along a tangent line, ensuring smooth motion. In physics, when an object moves in circular motion, its instantaneous velocity is always tangential to the path. And in engineering and design, tangents are used to construct roads, tracks, and even architectural curves for perfect alignment. So, tangents aren't just mathematical lines, they represent the real world connection between straight and curved motion. Alright, let's wrap this up with a quick recap. We learned that the number of tangents depends on the position of the point relative to the circle. If OP are, there are two tangents. If OP equals to R, there is one tangent. If OP are, there are no tangents. We also learned how to calculate the length of a tangent using PT equals square root of bracket OP squared minus a squared bracket close. And we saw real-life examples where tangent geometry applies, from wheels to gears and even orbital motion. And that's the beauty of geometry. From a simple circle, we uncover deep relationships that connect mathematics, physics, and everyday life. In the next video, we'll explore tangent theorems and their proofs, which take this concept one step further into the world of circle geometry. Until then, keep practicing and keep discovering the magic of math, one circle at a time.